The fundamental idea of describing a curve in space or a trajectory in space by a vector is that the head of the vector describes the trajectory as the parameter moves through its values from maximum to minimum. So we can see this vector describing this curve through space, and then we just allow each component to be the value of the function for that component. So that as we look at fundamental properties, for example, equation of a straight line, we can see that the value r is an initial point here represented by p0, and then a direction vector on which the parameter operates. So as I move the parameter here, then I'm describing that line no matter whether the parameter is positive or negative. Right, so that being able to find the equation of straight lines is a very important skill as we move forward in this calculus course. So that, for example, it would be easy enough to find the equation of the line described by these 2 points, P0 and P1. All I need is an initial point and a direction vector. But then now I want to look at what happens when the projection on the xy plane. So in other words, this plane here on the xy axis, we're going to project the line onto that plane. So you can see that there is no expression in z, and that all of the points are represented in the xy plane. So a good exercise is to try to find this vector and then calculate the projection using the dot product so that you come up with the projection of L in the xy plane. We can also do that in a different plane, in the xz plane, kind of in a similar way, and that think about, well, all it's going to do is just project on this xz axis, and that, again, another exercise, you can use the equation of this line again, but then project it onto the xz plane and come up with this. Notice that z is a function of x. Okay, so that as we start to get a little more sophisticated, we can get this roller coaster curve that is comprised of a cosine function in the x component, a sine function in the y component, and a modified sine function in the k component. So what we do then is think about, well, what is the projection in the xy plane? Let me just let it trace out the trajectory here so we can see the head of the vector describing the trajectory. And then now if we look at what happens in the x and y plane, let me kind of go down here and see if I can get right down the axis, right? So almost looking straight onto the x and z plane, you can see exactly what's going to happen. Cosine function in the x component, sine function in the y component, that's a circle. So unfortunately that label is kind of in the way, but if we set it in motion, we can see in the xy plane that the function describes a circle, as it seems like it should, based on the parameterization of the function. Okay. So in the xz plane and in the yz plane, we'll get a slightly different function because of the periodicity of the z component, right? Sine 2t. So that you can almost see right here what's going to happen is you're going to get this kind of infinity symbol when we move through that in the xy plane. So let me set it back to its minimum, and then as it traces out that parameter, you can see what's happening, and that's the interaction of the cosine or sine and this smaller amplitude, faster curve in the k component. The definition, one of the good things about you doing calculus in 3 dimensions in vector valued functions is that everything happens like you would expect it to, component by component. In other words, the derivative is the derivative of the components. The integral is the integral of the components. So one of the things that we just do is just to kind of motivate and talk about what is, you recognize this quotient here is the difference quotient, the kind of the beginning of the definition of the derivative. So that this is just a vector tracing out space, and if I do just a little bit of delta t, that as I move through space now, that point is going a little further, and I can talk about, well, here's the vector, let me move it back just a little bit, and that the difference vector, and then this change, the rate of change, right? So that this represents rise over run, basically, and that as we move through space, that rate of change describes what's happening to the curve, right? So as dt goes to 0, we get a tangent vector, right? The same definition that was applicable in one-dimensional Calc 1. Right, so now we're just putting it in 3 dimensions, and things kind of move around space rather than just moving in a 2-dimensional plane. The next figure shows what is meant by smooth. And when you read your textbook, that many of the definitions will start, well, let f be a smooth function. And a smooth function has analogy of being differentiable or not having singularities. Like this function here has this very sharp point at 0, so that this value of r of t becomes undefined, and this is not a smooth function because of that change, right? So that you get this cusp or corner point, which is analogous to the one-dimensional case where things are non-differentiable because of a corner. So that now we kind of look at what is meant by the unit tangent vector, and this is just a trajectory, a simple trajectory in space going described by this vector function here, and that now if I show the derivative, which is the rate of change of that function over time or as the parameter value changes, you can see this. And so it's a little hard to see because of this figure, but that the unit tangent vector, I'll turn off the tangent vector itself, and you can just kind of see the unit tangent vector, which is 1 unit long and describes the same direction as the tangent vector, but just is that kind of modified divided by its length. So it's a unit tangent vector. So this is kind of the first step in getting into our 3-dimensional frame of reference called the TNB frame, the tangent normal binormal frame, which is a 3-dimensional orthogonal set of axes that move along the trajectory with the value with the unit tangent, unit normal, and unit binormal vectors. And so that's kind of the getting through the rest of chapter 11, but this is the first step of it. Okay, so the next thing is that I just want to show you here this idea of what's going to happen to the velocity and the acceleration as we move through space. So here is a trajectory that's described by a vector-valued function. And if we just look at what the velocity and acceleration does, okay, let me move it back just here a little bit, and that one of the things to notice, so kind of identify what's happening in the trajectory in this section right here, around this curve. So as I go around this curve in space, so look what happens to the acceleration vector. So now what has to happen, right? So I'm here. Let me move just a little further there, so that as I move, I have to go in the direction to the right on this figure, over that way. So that if I don't have an acceleration, this velocity would continue and carry me out into space here. So that the description, or what happens to the acceleration, is that I have to have an acceleration to the right, or else I wouldn't turn to the right. Right? They would just continue on in a straight value, right, without acceleration. So that to start to work and be able to dissect the velocity and the acceleration are important skills to be able to work with. So that in a particular case with the velocity and acceleration, if we look at a circular trajectory, right? A is the amplitude, cosine, sine. So you should always kind of pay attention to thinking about, well, what is the orientation of this parametric curve? Which way does the graph go as t is increasing? And so that's one thing to keep in mind as you're working with circular functions in any kind of parametric description of a vector-valued function. So that now you look at what happens with the velocity, or r of t is the opposite of the acceleration, and that the the trajectory vector-valued function and its velocity are equal to 0 at all times. So as this goes around, right, so cosine is x, that's counterclockwise, and that, let me put the velocity on there. So the velocity in this case is going to be constant. I'm going around a circle, and no matter which direction I'm going, I am at the constant velocity, okay? So that to create this circular path, the acceleration has to be moving inwards. In other words, I put the acceleration on there, right, that I'm going to turn off the position, so that now the acceleration, as I go around this curve, has to be moving. You kind of would think about it to your left to keep going around in a circle, all right, like an Indy car driver or something. Okay, so this is an important concept here, is that for a circular trajectory, that the position vector and the acceleration vector are oppositely directed, and that the position vector and the velocity vector are orthogonal at all times. That's what makes a circle. For an ellipse, that's not true, because you have those kind of acceleration areas at the corners. Okay, so the final figure we're going to look to right now is this figure 94, 1194, which is about a baseball pitch. And so this is just kind of putting it into context here with the, let me get that back to the beginning there, is that we use these vector components now to think about, oh, whoops, I didn't, yeah, that's not what I wanted to do here, is that these components, okay, is that to go through this pitch here, this is what I wanted to do, is to pitch this ball down the path, right? So you can see on the bottom, the blue line is creating the projection on the ground, and the ball is then landing here, right? So this is the acceleration due to wind. And the correction angle here, as I have as a 1/2 degree, let me put it at 0, means that because of this crosswind, the ball would line off of my intended target. So now if I put this here at minus 1.21 and then run the same, that the ball would then go down the path, start out, you can see it diverges just a little bit right here in the middle, and then comes back due to the effect of this wind. Okay, so it's just kind of a three-dimensional example of how these components can add up and complete things, right? As you increase the wind or decrease the wind, you go offline and try to figure that out. Okay, so this is a little bit of a graphical introduction to lines and curves in space, which should take us through chapter 11.7 of the textbook. Okay.